Good morning, everyone. I hope everybody's doing okay today. We're going to be looking at the next lesson, and in order to get you ready for this, you need to have your notebook open to page 13 of the unit handout. Before we actually get to the lesson, though, I would like to just review what we did yesterday, which was dealing with sums and differences of functions, because you're going to find with what we deal with today, which are products and quotients of functions, that there are similarities to what we learned yesterday. To begin with here, this is all under the heading of function operations. So yesterday we dealt with sums and differences. Today we're going to be dealing with products and quotients. What we learned yesterday is that when you see this notation, f plus g quantity of x in the top left of the screen, it means you're going to take the function f of x and add g of x. The order in which you add two things doesn't matter. So if I write f plus g quantity of x and you decide you're going to write g of x plus f of x, and your neighbor decides they're going to write f of x plus g of x, doesn't matter. On the other hand, the notation that we use for differences is f minus g quantity of x, and that means f of x minus g of x. But the order is important here. You're subtracting the two functions, but just like numbers, the order in which you subtract things changes the outcome of the problem. So f minus g of x means f of x minus g of x. You cannot write that as g of x minus f of x. We learned there's this rule, I call it the domain rule, that the domain of either the sum of two functions or the difference of two functions is the common domain, the domain that's common to both of the functions. It's where they overlap. You cannot add two things together unless they both exist in the region on the grid where you want to add them together. We also learned, or I told you anyway, that we don't have any simple rule for finding the range of a function that is the sum or the difference of two functions. We have to go through the heavy lifting to get a graph of the new function to see what the range is going to be. This is perhaps the most important outcome of yesterday's work. What we learned is that what's happening when you combine two functions by addition is you're adding y coordinates. What this is saying is f plus g of a particular value of x is equal to f of that value of x plus g of that value of x. Don't get psyched out by this. I'm just saying that if I told you that a new function was f plus g quantity of x, and I said, what is f plus g quantity of 2? That would simply mean, since f plus g quantity of x is f of x plus g of x, f plus g quantity of 2 would be f of 2 plus g of 2. But you need to understand, I think it's really important, that you need to understand, there we go, that this is the y coordinate on f, and this is the y coordinate on g, and this is the y coordinate on f plus g. And this is my point. To find the y coordinate on f plus g, you're going to be adding the y coordinate on f to the y coordinate on g. That's all this statement is saying. A is a specific value of x. And similarly, we could go through the same explanation with the difference. I'm not going to. F minus g quantity of a will be f of a minus g of a, where a is a specific x coordinate. I explained this idea to you yesterday by saying that what's really happening here is that you're taking x comma y on f, and you're taking x comma y on g, and you're marrying these 2 points together to get a new point which is on the new function. And I'm going to focus my attention here on the sum rather than the difference. these 2 points marry to become x comma y of f plus y of g. So there's a number of ways I can keep saying the same thing over and over again. The bottom line is when you are operating on functions, it's the y coordinates that get added or subtracted. And leading up to today's lesson, the lesson is going to include when you're multiplying or dividing functions, it's the y coordinates that get multiplied or divided. Those 2 y values that you were looking at adding or subtracting may be found from equations. Maybe you know the equations of the functions. They may be found from a table of values. They may be found from graphs or any other descriptions of the functions. And as we get deeper into this unit, you'll see a number of situations where we have to do just that. So on page 13 of your unit handout, what are we going to be doing today? We're going to be sketching the graph of a function that is either the product or the quotient of 2 functions. We're going to be determining the domain and range of a product or a quotient of 2 functions and writing the equations for functions that are products or quotients. In other words, everything we did yesterday dealing with sums and differences, we're going to repeat today with products and quotients. To begin with, though, I want to talk about these 4 words. Rather than diving right into the lesson, we use in mathematics these 4 main words for the 4 main operations. There are other operations, but these are the main ones. Sum, difference, product, or quotient. We know that the sum of things is the result of adding them, and we know that order is not important. We know that the difference is the result of subtracting things, and we know that order is important. When you multiply things together, you get what's called a product, and the order is not important. You can do this with numbers to convince yourself 2 times 5 gives you 10, and if you switch the order and say 5 times 2, you still get 10. Quotient is the word we use to describe the result of division. So for example, 20 divided by 4 gives a quotient of 5. And we've used that word before when we dealt with division of polynomials. But the result of dividing is what we would call an order-sensitive operation. 20 divided by 5 gives you 4, but 5 divided by 20 does not give you 4. It gives you 0.25. There's another issue, though, that I want to talk about with these 4 operations. As long as you have 2 things that exist, you can add them. The sum of 2 defined values is always defined. If you have 2 defined values, 2 values or things that really exist, then you can always subtract them. And you can always multiply things that exist. But you cannot always divide by things even though they exist. The reason is division by 0 is not defined. So whenever we talk about a quotient, we have to consider the fact that the denominator can never be 0. And this is not a new idea. We've talked about this in Math 20 and in Math 30 earlier this year. Keep that in mind as we move forward. All right, let's get to the notation. Just like we have a certain way of writing the sum or the difference of 2 functions, we have a particular way of writing the product. It is, well, it's pronounced as f times g. There's no other way to say this thing that I'm going to highlight. This means f times g of x. But what it means specifically is f of x multiplied by g of x. And much like the work we did yesterday with sums and differences, when I see this thing that's highlighted up here in the top right of the screen, I automatically see this thing that's highlighted near the center of the screen. Please make a note that f times g quantity of x is the same as g times f quantity of x, because f of x times g of x is the same as g of x times f of x. Please make a note that when you're writing this down and you say the product f times g, that dot you draw is very clearly a filled-in solid dot. And that means product. And the reason is, if you draw like a little O that's not filled in, That symbol is not what we use for product. That symbol is what we use for something else that we'll learn about next week on Monday. The quotient of two functions is written as h of x equals f over g, quantity of x, and it simply means f of x over g of x. Nothing too earth-shattering so far. However, please make a note that f over g, quantity of x, and g over f, quantity of x, are two entirely different things because the order in which you divide items changes the outcome. One of these means f of x over g of x. One of these means g of x over f of x. And again, they're different things. The domain rule. Well, the domain rule of a product of functions or the quotient of functions is basically the same as the domain rule for the sum or difference. Namely, that whatever domain is common to both would be the domain of the product or the quotient. Just like with sums and differences, you basically can't add or subtract or multiply or divide things if those things don't exist. And remember, we're talking about y coordinates. There is an exception, though. The exception is that the rule is further extended by saying if you're dealing with a quotient of two functions, you have to remove the values of x that make g of x equal to 0. If h of x is f of x over g of x, which it is in your note package right here, what that means is that g of x cannot be 0. Because if g of x has a value of 0, you're going to be dividing by 0, and division by 0 is not allowed. I think it's worthwhile to make a note, even though we're not going to necessarily use this right now, that g of x is equal to 0 at x-intercepts. G of x, which is a y-coordinate on the graph, is equal to 0 whenever the graph is on the x-axis. So that means wherever the graph of g of x has x-intercepts, f of x over g of x will not exist. I want to run through, and these examples that I've got on the board here are not in your note package, but I would like everybody to follow along and get your brain working here this morning. I've got two graphs, f of x, which is in red, f of x, which is in kind of a bluish color, and g of x, which is in red. If I said to you, what is the domain of f plus g of x? Well, below the graph, I have a black number line that represents x. And essentially what this red line is a line that indicates that this red function, g of x, is defined everywhere x is equal to 5 or more. And we could even write that down. I could say that this is x is greater than or equal to, I think I might have just said 5, but what I meant to say was negative 5. On the other hand, the blue graph, and I don't have a blue pen handy, so I'll use black, has a domain of any real number. You can see that that blue absolute value function extends forever in both directions. So where do these two domains overlap? Well, they overlap in the region where x is greater than or equal to negative 5. Anywhere in that region, horizontally speaking, both functions exist, so you can add the y coordinates together. The same would be true for f of x minus g of x. You can only take the y coordinate on f and subtract the y coordinate on g if they both have y coordinates, and they both have y coordinates in that domain. The same with the product. You cannot multiply the y coordinates unless they both exist. Now what about f of x over g of x? Well, you can only divide the y coordinates where they both exist, except that at x equals negative 5, the y coordinate of g of x is 0. Give some serious thought right now to the coordinates of this point and to the coordinates of this point. Specifically the y-coordinates. The y-coordinate up here, this is at negative 5, comma 7. The y-coordinate down here, well, this is at negative 5, comma 0. F over g means you're going to take the y-coordinate on F, divide by the y-coordinate on g, but that means you take 7 divided by 0. And you can't do that. You can't divide by 0. So x is greater than or equal to negative 5 is not the domain. X is greater than negative 5 is the domain. We start off with the common domain and then we remove from it any value of x that makes division by 0 happen. If we use the same rule here for g over f, we would start off with x is greater than or equal to negative 5. But now what we're going to have to do is exclude from that domain these two x values because y there is 0 on f. And this function means g of x over f of x. So you can't do that if f of x is 0 and f of x is equal to 0 in those two regions. Pardon me, those 2 points. So how I would communicate this, and let's just say that they are at negative 1.5 and positive 1.5, I would simply put a comma and say, oh, by the way, x cannot equal to plus or minus 1.5. All right, let's go back to the lesson now. Example 1, consider these functions. What's the domain of each function? Well, f of x has a radicand of x minus 1, radicands must be greater than or equal to 0, which means the domain of that function is x is greater than or equal to 1. When you take a look at g of x is a linear function of y equals 1x minus 2. That means it's a line with a slope of 1 and a y-intercept of 2. Not much thinking goes on there. X must be an element of the real number set. Done. B, what is the equation of f times g quantity of x? Well, that simply means f of x multiplied by g of x. So what does that give us? It gives us h of x equals the square root of x minus 1 multiplied by x minus 2, and there's nothing to be gained by multiplying that radical into the x minus 2. It really doesn't do anything. What does the domain rule say the product will have for a domain? Well, on the one hand, f of x is only defined when x is greater than or equal to 1. So this is the domain for f of x. On the other hand, the domain for g of x is any real number. So where do they overlap? They overlap from 1 to infinity, which means the domain of h of x should be x is greater than or equal to 1. We are asked to confirm that with a graphing calculator. I mean, I wouldn't teach you something unless it were true, but let's just check it out to be sure. We're going to put y equals the square root of x minus 1, making sure to close the brackets on that argument for the square root. Then we're going to multiply that by, in brackets, x minus 2. You're not expected to know what this graph is going to look like. I'm going to go zoom 6 just as a starting point. And now what I'm going to do is zoom in a little bit. It seems as though there's some feature there that's important. I'm going to go zoom box and make a little stretchy screen that includes that x-intercept or x-intercepts. And that's what it looks like. And you need to be aware that your graphing calculator has limitations. It's not doing a stellar job of graphing this. particularly close to that x-intercept, but trust me that it does start at 1 and go around and up. So x is in fact greater than or equal to 1. C, well, what about a quotient? What if I said, what is k of x? K of x is equal to f of x over g of x, which means k of x is equal to the square root of x minus 1 over x minus 2. Use the domain rule to state what the domain would be. Well, if we go back and take a look at B, particularly we look at this region, this line graph for f of x and g of x for their domain, remember this is 1, these line graphs led us to the conclusion that x is greater than or equal to 1. Those two functions both exist when x is greater than or equal to 1. Unfortunately, 2 is a number greater than or equal to 1, and when we eyeball, this is your eyeball, when we eyeball x minus 2, you can see that since you're dividing by x minus 2, x cannot be equal to 2, which means x must be greater than or equal to 1, but not equal to 2. There are other ways you can write that, but I'm not worried about that today. Let's confirm this with a graphing calculator. This time we're going to take the square root of x minus 1 and we're going to divide by x minus 2. I'm going to go back to Zoom 6. This is what it looks like. I'm going to adjust my window settings to show you a little more detail. That's what the graph looks like. When you think about this in terms of asymptotes, you can see that there is a vertical asymptote at 2, which makes sense. There's an x minus 2 in the denominator. But what's curious is the graph starts just kind of bang in the middle of nowhere and then moves to the right. So this is consistent with saying x must be greater than or equal to 1, because here is where x equals 1, but x can't equal 2 because that's where an asymptote is. Example 2. Given f of x equals x plus 2 quantity squared minus 5 and g of x equals 3x minus 4, what is h of x if it's the product of the two functions? So h of x will be equal to f of x times g of x, which means h of x will be equal to, let's see, f of x is x plus 2 to the squared minus 5 times g of x, which is 3x minus 4. I hope everybody is clear on this large set of brackets and its necessity. I have to multiply all of f of x by g of x. So what I'm going to do first, and we are expected to simplify this, is I'm going to figure out what x plus 2 quantity squared is. Of course, x plus 2 squared means x plus 2 multiplied by x plus 2. So that's going to give me x squared plus 2x plus 2x plus 4. Then I have minus the 5. And then I need to multiply that by 3x minus 4. Simplifying a little bit further, h of x is equal to x squared plus 4x minus 1 multiplied by 3x minus 4. I'm just double checking my work. Now you have a trinomial multiplied by a binomial. What we're going to need to do here, everybody, is multiply the negative 1 by this binomial, multiply the 4x by the binomial, multiply the x squared by the binomial. I'm going to start with the x squared. X squared times 3x is 3x cubed. X squared times negative 4 is negative 4x squared. I'm done with the x squared. Moving on to the 4x. 4x times 3x is 12x squared. I'm lining it up with my other x squareds. 4x times negative 4 is negative 16x. I'm done. And after I'm done with all these, I'm going to double check all of them. And now I'm moving on to the negative 1. Negative 1 multiplied by 3x is negative 3x. Negative 1 multiplied by negative 4 is 4. Let me double check all of those. You should be double checking them as well. 3x cubed plus 12x squared minus 4x squared. Negative 3x, we also have the 4, we have the negative 16x. It's all good. So what this simplifies to, I'm just going to double check it again. I lost my train of thought there for a second. Negative 4x squared, then we have 12x squared, and then we have negative 16x, negative 3x, and positive 4. We're good. When we add all of these terms together, this is what we get for h of x. 3x cubed plus 8x squared minus 19x plus 4. We're asked, what is the domain and range? This has nothing to do with products or quotients or anything that we're learning today. This is a cubic polynomial function. It's an odd polynomial function, which means both arms are in opposite directions, and that tells you the range is any real number for y. Polynomial functions also exist over all real numbers for x. So x is any real number as well. Number 3, again, we're given two functions. What's the domain and range of a product? So h of x is the product, which will be x squared times 4x minus 5. I mean, there's nothing to that. That's what h of x is. What is the domain and range? Well, the domain is found by looking at the common domain. Y equals x squared has a domain of any real number. And for y equals root 4x minus 5, 4x minus 5 must be greater than or equal to 0. Which means x must be greater than or equal to 5/4. Just ruminate on that for a few seconds and make sure you know how I'm going from a radicand of 4x minus 5 to the statement that x must be greater than or equal to 5/4. What that's telling us is the common domain is x is greater than or equal to 5/4. For the range, remember that I've told you there's no nice rule for range. So we're going to use our graphing calculator to find the range. It's x squared multiplied by the square root of 4x minus 5. This will be nice because it will confirm to us what we suspect the domain is. I'm going to go zoom 6 again. Kind of a boring graph, really. I'm going to zoom in on that bottom part of the graph, get a little more information. Again, I don't know, some of you have better graphing calculators than the one I use here. But again, your graphing calculator kind of craps out when it comes to graphing things that are very close to the x-axis. But I'm pretty sure that that extends to the x-axis. Now, we said that the domain was x is greater than or equal to 5/4. 5 over 4 is 1.25. If I go back here, I can write x is greater than or equal to 1.25. So there ought to be a point at x equals 1.25. If I go trace 1.25, there is a point. It's like graphs of logarithms when we saw that in the last unit. Graphs of logarithmic functions get very steep, and your graphing calculator doesn't quite know how to graph steepness. Anyway, that's example 3. I believe we have one more example to go, and a little bit later on today, once you've gotten started on today's practice, Mrs. Lindahl will give you your next assignment, and your next assignment is related pretty closely to this example. And your next assignment will be due Tuesday, by the way. You're given two functions. One is a quadratic function, f of x, equals x squared plus x minus 6. One is a linear function, g of x equals 2x plus 6. By the way, both of them have domains over all real numbers. Determine the equation of h of x, which is g over f of x. All right, well, h of x is equal to g of x over f of x. That means h of x is equal to 2x plus 6 over x squared plus x plus 6, minus 6. All I'm doing is I'm writing what g of x is over what f of x is. There is an assumption here that when you are asked to write an equation of a function, you do it in simplified form. It's like, everybody, this question here where it said, determine the product of the two functions. We didn't just leave our answer here. We had to do all this hard work to get down to here to a single function. Well, we have to do the same thing here. Now, how is it we simplify this type of function? Well, it's a rational function, and in Chapter 9 we learned, and also in Math 20 you've learned, that the key to working with any rational expressions or equations is factoring. I can factor a 2 out of the numerator. I can factor the denominator as a product of binomials. I guess it would be x plus 3, x minus 2. Take a second or two and just make sure that you understand how that's factored. I'm not there to answer your questions, but I also just don't want you sitting there copying stuff down without thinking. If I expand that out, my outer product will be negative 2x. My inner product is positive 3x. Those add to give 1x, which is in fact what I have there. That makes me happy. What happens is the x plus 3's cancel, and here's where things get a little bit dicey. If you do that, and we haven't really done anything wrong here, but if you do that and you say h of x is equal to 2 over x minus 2, I hope everybody understands why that's wrong, even though the x plus 3's cancel. And for those of you that do understand why that's wrong, I would like you to add something to that function that we've got written there that makes it true. And hopefully in that 5 or 10 seconds that I've been waiting, many of you have written that x cannot equal to negative 3. That non-permissible value needs to be stated. By the way, since these x plus 3's cancel, you've got a whole at negative 3, which is what we learned in a previous lesson in this unit. I know that you also are aware x cannot be equal to 2. I mean, it's right there. This is your eyeball looking at it. But if you're going to go to the trouble of writing x is not equal to negative 3, why not also say, oh, by the way, it's also not equal to 2? Part B says determine the equation of k of x if it's f of x over g of x. So k of x is equal to f of x over g of x. And f of x, I'm going to write it down, but then I'll go back and double check because my memory is not always the way it used to be. I believe it's that. Let me just take a quick peek. F of x is x squared plus x minus 6. G of x is 2x plus 6. So the only thing that's different is they've been flipped over. Again, I can factor x plus 3, x minus 2. We can just look at what we did for the previous question. And 2, x plus 3. The x plus 3's cancel. So what we are left with is k of x equals x minus 2 over 2. Of course, we need to say that x cannot be equal to negative 3. And once again, because those x plus 3's cancel, you'll get a whole. By the way, and I'm just going to say this verbally and not write it down, but I think it's worthwhile to think about and understand. The reason there's an x plus 3 for a factor of both of these functions, this is y equals x plus 3, x minus 2. This is y equals 2, x plus 3. Since they both have a factor of x plus 3, they both have an x-intercept at negative 3. So whenever you have two functions that share an x-intercept, when you divide the two functions, you're going to get a whole at that value of x. The final question here seems very vague. It says analyze the two functions. So on the one hand, we had h of x equals 2 over x minus 2, where x could not equal to negative 3 or 2. I better just double check because I don't have your faces to look at to confirm this. H of x is 2 over x minus 2 with the two non-permissible values, whereas k of x was x minus 2 over 2 with the one non-permissible value. What does it mean to say analyze? It means what do the non-permissible values look like on the graph? For this one, you have a whole at negative 3 comma something, and you have a vertical asymptote at x equals 2. This goes back to the second lesson in this unit. When you have a non-permissible value whose factor cancels, that manifests itself as a whole on the graph. When you have a non-permissible value whose factor does not cancel, that corresponds to a vertical asymptote. Over here, we have a whole as well. It's at negative 3, but there were no other non-permissible values. The y-coordinate of the whole is found by putting the non-permissible value of the whole, the x-coordinate of that point that doesn't exist, in for x in the simplified function. If we do that, we get 2 over negative 5. So negative 2/5 is the y-coordinate of the whole there. If we put this into the x-coordinate for k of x into the simplified form, we get negative 5/2. That shouldn't be a surprise that the y-coordinates of the wholes are reciprocals because those two functions are reciprocals of each other. And as I said, I've been kind of keeping my eye on the clock, but I might have lost track here. I think this video is going to be about 35 to 40 minutes long. So you're going to have about 40 minutes approximately of class time today to work on some problems. And later on in class, probably with about 20 minutes left, once you've had a chance to get your teeth into these problems, Mrs. Lindahl will hand out the next assignment, and that next assignment is related directly to that final example. I hope that makes sense. I hope I didn't go too fast or too slow. And I also hope that you have a wonderful rest of the day and a fantastic weekend, and I look forward to seeing everybody on Monday. Take it easy.